Hey, everybody, and welcome back to another episode of Adventures in Machine Learning. This week on our panel, we have Miguel Morales. I'm Charles Max Wood from devchat.tv. And this week, we have a special guest, and that's Ather Fawaz. Am I anywhere close?
Yep.
I always feel bad saying foreign names because I'm like, I'm going to screw this up.
It's
say it wrong. Do you want to just introduce yourself real quick?
Yes, so my name is Ather, and I am a final year, so a senior at a university in Pakistan. And I am interested in computer science as my major tells. And I'm basically researching in quantum computers and deep learning.
Right. And it's interesting, this intersection, because I don't actually know a whole lot about quantum computing. I've heard and read a few things, but not a ton. And then machine learning on top of it. It's just like, okay, this is going to be cool.
It's basically the two biggest buzzwords that are in the industry right now. So it's an interesting combination. Yes.
When I went freelance, I was still only a few years into my development career. My first contract, I was paid $60 an hour. Due to feedback from my friends, I raised it to $120 an hour on the next contract. And due to the podcasts I was involved in and the screencasts I had made in the past, I started getting calls from people I'd never even heard of who wanted me to do development work for them because I had done that kind of work or talked about or demonstrated that kind of work in the videos and podcasts that I was making. Within a year, I was able to more than double my freelancing rates, and I had more work than I could handle. If you're thinking about freelancing or have a profitable but not busy or fulfilling freelance practice, let me show you how to do it in my Dev Heroes Accelerator. Dev Heroes aren't just people who devs admire, they're also people who deliver for clients who know, like, and trust them. Let me help you double your income and fill your slowdowns. You can learn more at devheroesaccelerator.com.
Absolutely. So do you want to just give us a brief introduction to quantum computing for people who have maybe heard the term but don't necessarily know what it is?
So we're all used to the classical computers that we have in front of us right now that are there in our mobile phones. So quantum computers, technically or very basically, if you can think about them, they're like an alternate mode of computation that allows a lot of different things to be made possible that wouldn't have been possible on the classical computer. And we're talking about ways and different ways of basically solving problems that would be possible on quantum computers. So since like classical computers are based on classical mechanics, we have transistors and all of that stuff, but quantum computers are based on quantum mechanics. And quantum mechanics has a lot of these interesting eccentricities within it allowed by the laws of physics that allow us to exploit them. And, we then reach a mode of computation that allows exponential compute power compared to classical computers. And another interesting sort of thing that we should get out of the way initially is that classical computers, they work on bits, zeros and as basically the most basic element of a computer. But quantum computers, they work on qubits, which are basically a short term for quantum bits. So qubits, unlike 0 and 1 of the classical bits, they have multiple states. So 0 and 1, but beyond those, they can be a mixture of zeros and ones and other states that could be represented within a qubit. So this is just a basic idea of what quantum computers are.
So quick question there, Ather. So I guess, early on, I was like, well, what is the difference between, quantum computers and, a regular computer? With zeros and ones, I can represent the 0 1s and, the probability distributions, right? But I guess what the main, breakthrough is here, that the qubits actually represent that to the hardware level. And that basically increases the amount of computation that you can have through this, same hardware. Well, I mean, if you compare bits to qubits, is that basically the advantage of quantum computers?
So I think before I directly answer your question, let's set some foundational principles. So quantum computers and quantum mechanics, basically they have this really interesting phenomenon. It's called quantum superposition, and by extension, we have quantum entanglement as well. So the first of those, quantum superposition, basically means that our qubits or our quantum particles, electrons, photons, or whatever of that sort, can be in a superposition, or can be in more than, or in a mixture rather, of multiple states simultaneously. Yes. So that is one key thing that we must understand. And secondly, there's this quantum entanglement property that allows us to basically entangle, as the word suggests, um, two or more particles in a way that knowing information about one particle automatically gives us information about the other particle, regardless of the distance between them. So, with these two things in mind, quantum entanglement and quantum superposition, this is where we can leverage these two principles and then make a model of computation that leverages these, that uses these to create or open opportunities for different models or algorithms that can be run on these computers to give us interesting solutions and pretty much faster solutions in most cases.
That makes sense.
So, what are the implications then of this for machine learning?
Okay, so let's just start with how a regular quantum algorithm or a quantum mode of computation would work. So you can think of it as when you have quantum superposition or quantum entanglement, you can create a mixture of all of these input possibilities or input combinations or input data, and then you can feed it at once into the computer. And when you have this parallel input to the computer right in front of you within one go, you can basically allow a lot of parallel computation within one go. So, quantum machine learning, as you would know, is a very emerging technology right now.
Mm-hmm.
And this is very, very new. So, the implications for for machine learning and deep learning, basically, the researchers are trying to figure out how we can create a mapping from our classical way of computation to a quantum way of computation. So there's this interesting paper that came out last year in October or November, if I remember correctly. It's by Amira Abbas and others. So their paper is, I think, titled The Power of Quantum Neural Networks. And essentially, they showed that you can train neural networks on quantum computers much faster, and one of the metrics of measuring how trainable or how effective a network is its dimensionality. So the dimensionality and the trainability both were proved to be superior to their classical counterparts on quantum computers. So what basically Amira and others did in that research, they used a real quantum computer to train a neural network of, I'm forgetting the parameters and the qubit numbers of the quantum computer as well, but they use a small quantum computer to train a neural network on the Iris Fisher dataset. It's a very common data set that we all use in machine learning and data science. And they realized that not only did the quantum computer, and by extension the quantum neural network, learn the parameters faster in lesser iterations, it also did not exhibit the dimensionality issues that traditional neural networks have. So that are two things that we have sort of realized or come across in the recent months. But there's a lot to be explored in this. And there are other techniques as well in machine learning, not only related to neural networks. We have multiple unsupervised algorithms like k-means and knns, right? K-nearest neighbors and k-means. We have quantum analogs of that, and those quantum analogs of k-means and knns and principal component analysis, all of those have shown faster training times and algorithmic complexities. So I guess not only does this mean that quantum computers can effectively, if they are put to good use, and if we can devise the quantum algorithms, they can have give us more powerful models and modes of computation. But also we can translate this mode of computation to basically give us quicker outputs and faster and lesser demanding on lesser demanding hardware.
So I would say also, well, it sounds like this would be pretty good too for more like black box optimization methods, such as genetic algorithms, particle optimization algorithms that can find the different, parameters to a network, for instance, and then basically, doing like a brute search type of that would be, very useful for that. And also, I would say that along the same lines that for reinforcement learning, you have a lot of now simulations that you can run in parallel, right? And then just roll out all the different possibilities in the simulation and then train using that data, which, would be pretty powerful. I don't know maybe, if there are any algorithms implemented, reinforcement learning algorithms implemented in a quantum machine.
I haven't come across those, but I'm pretty sure people would be working on those. But related to something that you mentioned, where you would have an optimization problem, where you would have a lot of multiple, what can you say, answers or solutions to a problem, and then you have to find the best or the optimal solution to it. So those are known as the category of optimization problems. And turns out quantum computers really excel in that, because when you have, like I said, you can have this multiple solution space and this mixture of solution space. You can feed it into the quantum computer right away, parallel, and then ask it, okay, give me the best answer. This is a very, very basic watered down view of how you would go about it. So I have seen quantum analogs of the traveling salesman problem. It's a very famous problem in computer science. It's basically you have these bunch of cities, and a salesman or a salesperson, anyone who has to visit these cities one by one once, and they have to visit all of these cities in the most
Mhm.
economic or feasible way. So this is a hard problem, and it's not that easy to solve classically. We don't have a very set, most optimal solution for it yet. But quantum computers, it turns out, the way we can use superposition and entanglement have proved to be very useful in this. And optimization problems of this sort are right up the alley of quantum computers, like you mentioned already.
This is really interesting. One thing that I'm wondering about is, so it sounds like people are out there implementing this on quantum computers. I mean, how common are quantum computers that people can go and experiment with?
Yeah. So quantum computers, IBM, Amazon, and Honeywell, Zapata, and Rigetti, all of these companies with friends are basically connecting their quantum computers that are sitting in their research labs at cryogenic temperatures. They're connecting these to the cloud. So you and I can go right now on their links and make an account, and we can run our quantum algorithms on real quantum hardware right now. And you don't need any fee for that. I think IBM Q has their 3, 5, and 7 qubits computers connected on the cloud. And what they are doing right now is, since we have a bunch of users that all can sign up and they basically enter a queue, and you take your place in a queue, and then you say, okay, whenever you get the time, run this job for me and give me the results. So you're in a queue, and then whenever the quantum computer is free, it will execute your job and give out your results to you. So currently, yes, you that is the only way of connecting to quantum computers with quantum hardware. But people are trying to make them more feasible. People are trying to make them commercially viable. But the other thing is that you don't always need a quantum computer to run your simulations. IBM Q and all of these other companies, like I've already mentioned before, they provide their quantum simulators that you can run right now on your computer. Although that is a very taxing thing to do, and it's not very easy to simulate quantum computers classically, you don't need real quantum hardware to actually run your experiments and check if you're getting the good results. You can run those quantum simulators. They use distributed computing to run your thing quickly. But like, yes, you have these two options: quantum simulators and quantum hardware. Actually,
So, quick question about that. So, if this is a different kind of hardware, do you need different kind of compilers, different kind of software, or have they implemented basically, I guess translation layers so that users accustomed to say Python can access through a Python package? Just
yeah,
yeah.
that is exactly what they've done. And one of the libraries that IBM has developed is known as Qiskit, and it's this quantum computing library with which you can write regular code in Python, and that will be translated by the Qiskit compiler or whatever backend that they have, and it will run on their backend. There are other companies and other frameworks like there's TensorFlow Quantum. TensorFlow, as we all know, we're all familiar with it, but there's this quantum analog of that as well. That is also written in Python, and I think there's the JavaScript version of that as well. But I'm not sure about that. There's Penny AI. It's also using TensorFlow Quantum. There's Google Circ. There's Q Sharp by Microsoft, like C Sharp. It's Q Sharp. So all of these are high-level languages or frameworks, you can say, or libraries with which you can use regular computers to code quantum computers, and then obviously that job will be done when compiled and executed on real quantum hardware.
That's awesome. I'm looking forward to running this emulator right next to the NES emulator I have on my computer. So I'm also interested in, so quantum computers still feel like they're somewhat in development, experimental. So are there advancements that we're looking to have in quantum computing over the next, I don't know, 2, 3, 4, 5 years that will make this, it could, I guess, that could change the industry as far as how we approach some of these machine learning problems and other problems out there in the world? Because, yeah, I keep hearing that, oh, it computes all this stuff way faster and it's more efficient in these ways. And so it just seems interesting that, okay, I could conceivably train a neural network or, do reinforcement learning or, pull in some of these other algorithms, right, to figure out problems that it would take years to train and then use a model on a conventional computer. They make it sound like you could conceivably do that in weeks or months instead.
Yep. But there are some caveats right now. The current quantum computers that we have right now, so basically the era that we are in right now is called the noisy intermediate scale quantum era, or NISQ era for short. So as the name suggests, we're in this era where our quantum computers are not perfect. And what do I mean by that? Is that the algorithms that you run right now, they might give you the correct answers, or it will be likely to give you the correct answers, but the answers could be better. And but in like some situations, the answers might be muddled down as well. So let's take a deeper look into what we have right now. The qubits would, however you might represent them in a quantum computer, one of the few ways, like 2 to 3 ways of representing them would be using the spin of an electron, or using photons, or using trapped ions in a lattice. These are multiple ways of representing qubits in a quantum computer, unlike the transistor that we have in a classical computer, or one low or high voltage. So the issue is keeping these qubits in their superposition is a very hard thing to do. And the entire thing that you base your quantum computer on is the fact that you have this superposition and you have this mixture of states. And when you lose that mixture of states, when you lose that superposition, it sort of becomes very hard, or it renders the quantum algorithm useless at that point. So the issue that we face right now is, how do we keep these qubits in a superposition? And the way, or the reason they lose their superposition, is that they interact with the environment. These are very small particles, and we are limited by hardware or our scientific techniques right now, that we are not able to isolate these qubits even at temperatures close to absolute zero. 3 to 4 degrees centigrade is basically what they operate on, but even then they're not free from interactions from the outside world. So once you so this is where we are at right now. We're trying to fix this problem of decoherence. This entire thing of the entire qubit losing its state is known as decoherence. So we at this point we're trying to solve this problem of decoherence, and this is a research problem at this point in time. This is a problem that requires multiple revolutions in our hardware, in our existing hardware. So it's not as simple as taking regular reinforcement learning, deep learning, or any other transformer model or neural network, and just taking that, implementing it on a quantum computer, and getting the results. So that is the challenge that we face right now.
So quick question there. If so, the long-term future, let's say, of quantum computers, will quantum computers replace our current computers, CPUs and GPUs? Is it more like sort of, GPU type of, quantum? I guess you mentioned the parallel aspect of it, right? And then, GPUs are pretty much, that's what we use GPUs for at this point. What is the kind of the future that you see there in terms of replacing these technologies?
Mm-hmm.
That's an interesting question, and one that is asked quite often whenever you're talking about quantum computers. But I think quantum computers will not be replacing our classical computers anytime soon, or I think even in the future. And it has certain caveats to it, basically. Quantum computers won't be faster for every regular task that we run on our classical computers. They won't be faster for our Zoom calls. They won't be faster for adding two numbers. They won't be faster for carrying out those elementary operations. So there is
I want the quantum Zoom call. That would be cool.
We could be have some superposition or entanglement. That's not good.
There we go. It feels like time travel or something, right? I'll go talk to myself in the past on my quantum Zoom call. Dude, don't do it. Don't do it.
Say that. That's not a good joke.
So yeah, I mean, they won't be replacing those because they're not faster at these regular traditional operations. The thing that I think the correct way, or the way that seems more fathomable right now, would be that these two modes of computation, quantum computation and classical computation that we have right now, these will work in conjunction. So problems that are built for quantum computers that are basically by nature inherently quantum, they will be run on quantum computers. But regular other traditional stuff, we have distributed computing, we have classical computers pushing the envelope year in and year out. I think those will develop in tandem.
So it's kind of similar to how we use right now the GPUs, right? Because I mean, if I want to run something on the GPU, I just say go ahead and run this piece of code in the GPU, and then I can run the rest in the CPU, because it doesn't make sense to run in the GPU.
Right.
So
I need this parallelized. I don't want that parallelized.
Right,
yeah.
Right. You're going to have access to that quantum now. But then are GPUs in trouble? At least in the machine learning realm, right? Because if I can run parallel computation that is, in many, many, many more states, perhaps as opposed to using a GPU, I just use a quantum computer. I mean, in the case that, that is accessible to all of us at one point, right?
Even with this, I think it will be a very difficult thing to surpass GPUs. The issue that currently we face with quantum computing right now is we don't have that many qubits. And for quantum computers to become very feasible commercially in training these large neural networks, take for example a GPT-3. It's basically trained on OpenAI's GPT-3. This transformer model is basically trained on the entire internet, and it's to have this sort of computational power at your expense, you would need a lot of qubits, and that amount of qubits is basically, for all intents and purposes, inaccessible to us right now. And even if we would have that, translating your classical piece of code, or like Charles said, I want this parallelized, I don't want this parallelized. And I think the issue with that would be it's not that easy to convert from classical code to quantum code. And there is some research coming out that is suggesting that it's not that easy to train quantum. Basically, I think we can cut this out and I'll fix this. Yeah. So can you repeat the question?
Yep.
So whether, I guess the question, the very first one, which is whether, I guess in the future, we're going to be replacing GPUs. And by the way, I actually didn't even mention TPUs, right? But there's also such thing as tensor processing units, right? So I guess my question is, like, how is quantum computing, and if is going to replace any of these different, sources of computation, right? Either the CPU, then the GPU, and the TPU. If there is any, in the future, that roadmap exists.
To answer that question, we would first need to understand where we are or what we need to make quantum computers very powerful. So to train big neural networks or to carry out very big computations on large amounts of data, it would be necessary to have a large amounts of qubits. So We don't have that right now, and that is inaccessible to us at this current point in time. But even if we had that, if we had thousands and millions of qubits, which is what people are building towards, what firms are building towards in the next few decades or so. But the issue with that is converting a piece of code, classical piece of code, to a quantum code is not that easy. And unless we can find those optimal ways or those optimal mappings of classical problems or the way that we solve those problems classically, they won't run any faster on quantum computers. So, inherently speaking, when you change the model of computation, you inherently change the way that you will be solving that problem as well. And this is something that you can sort of start appreciating when you uh, dive into how quantum computers or quantum algorithms are basically written. And I think if we have one way of, like, if we have some time for that, I would like to expound upon how we go about solving one of these problems. So, in an unsorted database, in an unsorted array, in an unsorted data, for example, we have to find a single element or a single object within that unsorted database or array. So that is the problem at hand. On a classical computer, you would do a linear search. Since the data is not sorted, you can't use binary search or any other heuristics about the data. If it is unstructured, unsorted data, you can't do any of that. And a linear comparison of that existing element of that, when you run a loop basically on all those array elements, you would say, okay, if the current element is the one that I want right now, then return that current element. That's basically how you would do linear search in an unsorted database on a classical computer. And this is basically going to like O of n by 2, roughly half the times you will need to run the algorithm for. But on the quantum side of things, the Grover's algorithm is basically a quantum algorithm that allows you to search an unsorted database in O of square root of n. And that is completely out of the ordinary at one point. I mean, that strikes you, if you don't know how it works, it strikes you, how can this be possible? You will have to check at least half of the array in the average case. But
Mhm.
what the Grover's algorithm is telling you is that you only need to check O of square root of n elements if you had n elements in an array or an unsorted database. And the way that you do is you don't do a linear search anymore. You don't do binary search anymore on or any of the classical computer algorithms of that sort. For that quantum algorithm, you would need a state space, then you would reflect to that optimal state space, and then you start watering down your solution space to give you the actual index position or the location of that array element or that object that you want. So that is basically how Grover's algorithm works. Unfortunately, I cannot dive into the details of that since that will need a lot of foundational physics and mathematics. But that is how you cannot execute this on a classical computer. So when you change the model of computation, you would need to come up with an exciting or a faster way of computation that does the same thing but in a different way, and that leverages the superposition and entanglement capabilities of quantum computers. So that is the sort of like the drawn out answer to your question, which was whether we could see a replacement in the quantum realm for GPUs and TPUs. Unless we find that mapping, unless we find those faster algorithms, it won't be that necessary to replace quantum computers, or it won't be that feasible to use quantum computers instead of TPUs and GPUs.
So that means don't sell your Nvidia stock, right? Well, we don't give financial advice, but
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
no. So quick follow up with that. So how do you envision quantum computing being used in the future as a separate then source of computation? And folks that We implement algorithms. They implement it for quantum computing, top to bottom, and then I just run against that particular machine. Or you see it a little bit more of a hybrid. I mean, if I have a Python package and, at work, I do have actually access to quantum computers, right? So I'm going to say, I'm going to be able to use that quantum computer to do some portion of my code. And I use, let's say that I now, implement some, code that uses all the qubits and all the goodness of quantum computing. Then I could basically run a piece of code to, run on the quantum computer. And then the rest of the code that I want to run, the 2+2, I just run in the regular CPU. Is that how you envision it? What, like separate or actually like a hybrid?
It can be a mixture of both as well, in the sense that we have variational quantum algorithms right now at this point in time, optimization algorithms at this point in time, that use both a classical part to them and a quantum part to them. So within this one algorithm or within this one solution to a problem, we have both a quantum part and a classical part. But obviously, if we take a look at it literally, yes, those two parts are separate, but they will be used in conjunction. And I think it would help to illustrate one specific algorithm here, variational quantum eigensolver, VQE for short. This algorithm basically what it does is in quantum chemistry for like our chemical reactions and all of that stuff, you basically to optimize our chemical reactions, it would be beneficial for us to run or to know or to be informed about the lowest possible energy state of our molecules that we are sort of trying to react. And this again is a very hard thing to do classically on a classical computer. So what a variational quantum eigensolver does is that it takes in it's basically a machine learning problem. Is again, it's a quantum machine learning algorithm, and we'll go into that just in a moment. It takes this state of our molecule and returns the lowest energy state of that. And the state of a molecule can be represented as a matrix, a Hamiltonian, which is then fed into this quantum algorithm. And then the quantum computer or this entire VQE algorithm, it will return the eigenvalue uh, associated with the eigenvectors, which will have the lowest amount of the energy for that molecule. So the way that you would go about this is you will have a quantum part which will search the entire state space of all the possible states of the molecule, which is what we're trying to do. We're trying to search through the entire state space of that molecule and return the state with the lowest possible energy of that molecule, the stable or the most lowest possible energy. So searching through this without any guide or heuristic would be again a very difficult thing to do. You're doing brute force search at this point in time. So we tried to make this. What people have done is that they've come up with a quantum with a classical half of this algorithm, which basically helps you optimize the searching via the quantum bit. So the classical part of this, the ansatz, is what it's called. The ansatz basically trains the parameters via which you will search through in via quantum computation in that search space. So using gradient descent, the classical bit, the classical half of the algorithm will basically optimize the parameters of the quantum bit, and and with those optimized parameters, the quantum algorithm will then search through the state space in a much faster way. So yes, those can be quantum computers and classical computers can be used for separate modes of computation and separate problems as well. But within the same problem, we can have situations where we would need both to work optimally towards the solution.
That's pretty cool. Yeah.
So I guess my next question is, let's say that after we're done talking or after the listener is done listening, somebody's like, you know what, I just want to go nerd out on this stuff for a couple of days. Like, where do people go to get more information about this stuff?
So yes, it's an interesting space that we are in right now. Quantum computers and a lot of the literature right now, they're trying to make it more accessible to the general public right now. But I will be honest, it is sort of academic right now, but that is something that they're trying to change. So as recently as last year, IBM held their Qiskit summer school in summers last year, 2020. What they did
Mhm.
was had this they had a bunch of kids. They came in, they taught them in a 4 to 5 week session, or perhaps more than that, 2 months, I guess. Or, but like regardless, what they did was they trained these people in their summer school. They gave these lectures from people who are within the quantum space right now, and they publicized these lectures recently in the last few months. So those lectures are freely available for anyone to watch, and they don't expect you to have more than mathematical understanding more than that of a high school level student. Yes, college level linear algebra would help, but that is not what they expect. So that is one place you can go to watch video lectures, and those lecture notes are available freely as well. The exercises are available as well. But the other way you can go is you can go on Archive, you can go on Google Scholar. There are a lot of survey papers and papers that describe quantum computers and quantum modes of computation, and by extension, these algorithms within them. So they will start from the basics. They will start from the linear superposition, linear algebra, all that foundation that you need. And then they will transition into how we can use superposition, entanglement, and design quantum algorithms of that sort. That is the second thing. But yes, I mean, these two places, research papers and courses taught by IBM or Amazon, or reading up the documentation of Qiskit or Amazon Bracket or Cirq or TensorFlow Quantum, that is where we are at right now. We don't have a very, we don't have a lot of great content that would help people who are beginners, who are amateurs at this point in time, to get into this space without much hindrances. But that is certainly that is something that they're working towards in the coming.
I I think your article is pretty good too. So, I mean, I would recommend that. One thing that I was going to ask is how about, quantum computing related to machine learning? Because it seems that these courses may be like, the general, but let's say that, you take that course and then are there any tutorials or books or anything that you recommend?
In quantum computing, to basically understand quantum machine learning, you would need to understand the traditional quantum algorithms first. And the way that these courses or these research papers are structured is that they'll go through the mathematics, and then they'll go through these traditional or well-known algorithms for quantum computing. So they'll start with the very basic algorithms, the Bernstein-Vazirani algorithm, Grover's algorithm, Deutsch-2's algorithm. But you will need to realize the importance of when we change the mode of computation, we inherently have to change every single thing about the algorithm, or our approach to the algorithm rather. So I think you can, once you have that foundation built, then you can start building towards looking into how these these libraries or frameworks define their quantum subroutines for these quantum machine learning algorithms. Qiskit has a great documentation of quantum machine learning algorithms as well. Amazon is sort of slowly building up their documentation for their quantum computing engine AWS Bracket. And Penny Lane AI, it's another firm that is basically also working on bringing people more towards quantum machine learning. And it's basically using TensorFlow Quantum as well. So, yes, the literature on this, it's not that accessible, but I think if you go in a linear way and sort of go from the ground up, then I think you will start finding resources on these.
Great.
Cool. Was there anything else that we wanted to dive into here before we go to picks?
Let me check. Yes. So one of the interesting things that the plan that we have in front of us right now for quantum development is that first, to realize commercially scalable quantum computers, we need to increase the count of qubits. And companies are working towards that. IBM and Amazon. IBM is most famous for this, and they recently released their quantum development roadmap as well. So their roadmap is basically the path forward that they have towards achieving commercially scalable quantum computers in the next decade or so. And the way that they are going about this, we're in 2021 right now. So by 2022, They want to increase our qubit count to around 400, 500 qubits. And by 2023 and beyond 2024, they want to go into thousands and probably millions of qubits. And this is the point where if we can control, our commercial quantum computers will become more scalable and more commercially feasible. So that is the exciting journey that we have ahead. And that is the point, if we reach those thousands and millions of qubits, then that is the point where we would have real time commercial scalable applications that all of us can benefit from, that businesses can benefit from, and that researchers can use to solve problems. That is,
Mhm.
I think, that is something exciting to look forward to.
Cool. Yeah, that's exciting because I can just see, and we've seen this in other industries, right? As some of these technologies become more available, all of a sudden we find new ways of doing things, and so I love the expandability, I guess, of qubits and thereby quantum computing to the point where it's okay. Well, I've got this sort of unconventional thing that I just couldn't get prioritized on the limited number of qubits that existed in 2020 or 2021, and now I've got my own little set here that I can go and kind of throw whatever I want at it. And hey, look, we figured out a new way to um, I don't know. I mean, let's go nuts, levitate cars or, cure this disease that's been plaguing people or, um, you know,
Yeah.
triple our agricultural load so that we can feed more people or, I mean, whatever, right? Or maybe it's just a novel way of communicating with people across the globe. I mean, who knows? But
Yeah.
yeah, it's interesting when people, because with a limited number, we kind of tend to prioritize things according to what we think will work out. And when people can go and do the crazy stuff, a lot of times the crazy stuff winds up not being so crazy and we get really interesting things coming out of those.
Yep. And I think quantum computers can have real practical applications, especially in the health domain. Like we all know, DNA folding, protein folding is one
Hmm.
of the hurdle problems that we have at hand right now. And it will tell us a lot about the structure of organisms of our genome. So quantum computers, since it thrives on problems that have multiple solutions and searching multiple or this gigantic database or the solution space rather, um, I think we can use quantum computers to actually make revolutionary changes in protein folding and genome studies as well. So that will help, and that will have real health, and that will have real beneficial changes
Hmm.
and impacts on the health industry.
Yep. Very cool. All right. Well, before we do picks, how do people find you online? I'm assuming you're on like Twitter or GitHub or places like that.
Yeah, I'm on both. On Twitter, my handle is at Ather Fawaz, and on GitHub, it's also the same, github.com/Ather Fawaz. Otherwise, I write regularly on neowin.net, and I cover news related to artificial intelligence, machine learning, deep learning, quantum computing, and space travel in general. But also anything else that catches my eye, I will cover that as well. So those are the three ways: Twitter, GitHub, and Newwin that you can reach out to me from.
Cool.
And I noticed you're located in Mars, right? Is that right?
Yeah, I changed
It's
my bio location when the Perseverance rover landed on it.
Nice. Yeah. Otter is up there hanging out with Mark Watney. So I freaking loved that book. All right. Let's go ahead and do some picks.
Hey, folks, I don't know if you've noticed, but I've been working a lot on figuring out how to help people become the most valuable developers on their teams or becoming the top 5% of developers in the field. If you're looking to level up, figure out how to contribute more, get the career you want, get the career that you want that will support the lifestyle you want, then you should check out the Most Valuable Dev Summit. I've invited some of my friends across the community, people that you've heard of, people that have worked on systems that you use on a daily basis, people who have invented new ways of doing things over the years in programming. And I've asked them one question, and that question is, how do you become a top 5% developer? How do you become 1 in 20 of the best developers out there. And so we're going to go ahead and have that conversation with them in interviews on the Most Valuable Dev Summit. And you can find that at summit.mostvaluable.dev.
Miguel, do you have some picks for us?
I do have one. Actually, just came across this book by Warren Powell, Reinforcement Learning and Stochastic Optimization. Sorry, guys, I'm always going to do reinforcement learning stuff. So,
it's all good.
That's what you get with me. My bad.
Nerd.
But I realized he's working on this book. It's available for free online. I cannot do that with my book. So I still recommend my book as well. But I think his book actually, it gives you a different perspective in reinforcement learning. I think one of the issues with reinforcement learning is that there are so many fields that care about optimal decision making, right? I mean, that's kind of obvious.
Mm-hmm.
Finance, right? So economics, you have even, psychology. You have just so many fields. This one in particular is a kind of operations research approach to optimal decision making. But now I love this, that even those guys are talking about reinforcement learning nowadays, right? As opposed to just operations research, the way they used to talk about this. So the subtitle is A Unified Framework for Sequential Decisions, which I find intriguing. I have not read it myself. I read his previous book, but I'm going to pick this one because I like to read this one and see how they're doing and how they're, unifying, the problem of optimal or near optimal decision making.
Awesome. I feel very unified now. So
that's nice. You're entangled.
That's right. I'm entangled. I'm going to go down to the quantum realm with Ant-Man and get entangled in some. Anyway, I've got a few picks. My wife and I don't know if I'm still trying to decide if I liked this movie or didn't like this movie. But last night for our date night, we put on The Circle with Tom Hanks and Emma Watson in it. And it kind of talks about some of the social issues of, sharing and where it can go. It's a movie that was made a few years ago, and it's always interesting to see how some of the social commentary on technology ages, right? And this one I thought was really interesting, just in the sense of everything that the internet can do, and the way that it affected people's behaviors and, the way we're all connected and stuff like that. The Circle is basically a stand-in for social media on super steroids. And anyway, just fascinating stuff. The thing that really threw me, honestly, with the movie was the ending. Because it kind of go on this journey with Emma Watson's character. I think her name is May, and at the end, right, she kind of, exposes the bad guys for who they are,
don't
right?
Don't spoil it. Are you spoiling the movie?
I figure if it's been out for a year, it's fair game.
Okay.
But anyway, so at the end, and then at the very end, it didn't seem like, I don't know, I didn't feel like I got the payoff, right? Because, they're giving you this messaging about, the value of privacy through the whole thing. At least that's what I was getting out of it. And then I didn't feel like they paid that off at the end. So that's kind of my issue with the movie more than anything else. But it was definitely interesting to see, okay, what are the implications for what we expose online and what we expose of other people online, and what our relationships are like and how it's impacted by these types of social networks. So anyway, if
episode.
What was that?
It's basically a Black Mirror episode, right?
Yeah, kind of. Yeah. So anyway, it was interesting to watch. There are a whole bunch of documentaries out there that kind of have a similar messaging as far as privacy and the implications of this stuff and what information they're collecting. The Social Dilemma is one that I liked. There are a few others. I'll have to pull those out and I'll pick them next week.
I think that's actually super interesting. It's my view is that there is a problem there that we are not yet capable. We're not understanding. Really, we're not understanding the consequences, the long-term consequences of, not just putting yourself out there, social media, but also relying on that for, friendships or, interactions and day-to-day information gathering and so on. once you just remove yourself, and there are a few books. I'm not gonna pick after your pick, but there are a few books.
Oh, go ahead.
Well, there are a few books that are really interesting, like in the Shallows, I guess, is one of them. There is an author that is pretty good. Deep Work is another book that basically these guys don't even use social media at all, right?
Right.
And it's just so very interesting because you kind of already use social media is part of your daily life kind of thing, and there's actually a world without it. But yeah, no, I think it's a super interesting topic.
Yep, absolutely. As far as other picks go, I mean, we're still doing the accelerator, devchat.tv/hero. I'm getting ready to launch a podcast related to that. So if you're looking to build a following, I had somebody actually ask me, is this for people who already have a following? No, it's not. I mean, if you already have a following, bonus to you, right? We're going to still walk you through starting a podcast and, building your reputation so that you can get where you want to go with your career. But if you don't have a following, I don't think any of the people I'm coaching right now as part of the accelerator actually currently have any kind of following. And so we're working on that. And that's been really fascinating too. So I'm going to pick that. And then I've been spending a bit of time playing with Docker, and the Visual Studio Code extensions for Docker are awesome. So I'm going to pick those as well, as far as just the tools. So there you go. Ather, do you have some things you want to shout out, let people know about?
Let me check. First would be the Qiskit textbook. I think if for people who really, really want to get into quantum computing, I think this is a great textbook that you can find for free online. And it has bits of code as well. And it dives into quantum computing from the basics too. So I think it's a great starting point. And you can use this in conjunction with the lectures that they've already released online from the Qiskit Summer School previously. And there's this other, hold on a second. I'm a big fan of Formula One, but that's something that won't be academic. But like my recommendation would be to watch this Netflix dramatic documentary on F1 Drive to Survive. It's this dramatized take on the lives of Formula One drivers, and I think it's pretty interesting, pretty dramatic, and it comes out yearly based on every season. And the season that just came out today, season 3. I think I watched the first episode, and it was pretty exciting to watch. So that would be my pick, my second pick.
Cool. Yeah, I was actually on a racing car team in college, and it's kind of interesting. It was an engineering challenge. It was electric vehicles, but it's definitely interesting to see how all that works. And I'm sure Formula One is a bit different, but in some ways there are similarities. And it was interesting to see how it kind of influenced, vehicles coming out over the years. So, yeah. All right. Well, thank you, Ather. This was awesome. Yeah, I want to go just spend a little more time just nerding out on this stuff. We'll see if I find the time. But thanks again for coming and sharing with us. And
for having me.
Yeah.
I applaud that. Thank you so much. Very interesting conversation. Appreciate it.
All right. Well, we'll go ahead and wrap this one up. And until next time, folks, max out.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CacheFly.com to learn more.